Hello coders, I welcome you all. In this video, we are going to perform big Mart sales prediction using machine learning using real-world dataset available on Kaggle. You can download this dataset from Kaggle or from my GitHub account. Link is given in the description of this video. So let's get started. So let's first import the libraries that we required. We will import others when they are needed. So let me first import pandas as PD. Also let me import numpy as NP. Also let me import shebon as SNS. Let me import matplotlib.pyplot as PLT and let me import warnings. Let me execute this cell. As you can see, our required libraries are successfully imported. So let me write warnings dot filter warnings and let me pass here ignore. So this code disables warning in Python. Let me execute this cell. Now let's load our dataset as pandas data frame. So let me write pd dot read underscore csv because our dataset is available in .csv file format with name big underscore mart underscore train .csv. As I said, I have downloaded this dataset from Kaggle. You can download this dataset from Kaggle or from my GitHub account. Link is given in the description of this video. Let me execute this cell and let me assign it to one variable. Data is equal to this statement. Let me execute this cell once again. As you can see, we have successfully loaded our dataset as pandas data frame that you can see over here. So let's display 5 random rows from our dataset. So for that, we have to write data dot sample and let me pass here 5. Let me execute this cell. As you can see here, in pandas, this sample method is used to randomly select rows from a dataset that you can see here. We have selected 5 rows from our dataset that you can see over here. This is our dataset having this many features. And this is our target column, item underscore outlet underscore sales. So we are going to predict this item underscore outlet underscore sales. As you can see here, to predict this, we are having these many features. So the data scientists at Big Mart have collected 2013 sales data for 1559 products across 10 stores in different cities. Our aim is to build a predictive model and predict the sales of each product at particular outlet that you can see over here. Item outlet sales. As I said, this is our target variable that we are going to predict using this many features that you can see over here. As you can see here, our first feature, item underscore identifier, which contains unique product ID that you can see over here. Let me execute this cell once again. As you can see over here, item underscore identifier. As I said, it contains unique product ID. As you can see here, item underscore weight, which contains weight of product that you can see over here. Now next, item underscore fat underscore content, which contains whether the product is low fat or not that you can see over here. Now item underscore visibility, which contains the percentage of the total display area of all products in a store allocated to the particular product. Next is item underscore type, which contains the category to which the product belongs that you can see over here. Now next, item underscore MRP, which contains maximum retail price of the product that you can see over here. Next is outlet underscore identifier, which contains unique store ID that you can see over here. Now outlet underscore establishment underscore year, the year in which the store was established. And next is outlet underscore size, the size of the store in terms of ground area covered that you can see over here. Small, high, medium, likewise. Next one is outlet underscore location underscore type, the type of the city in which the store is located that you can see over here. And the next one is outlet underscore type. It shows whether the outlet is just a grocery store or some sort of supermarket that you can see over here. Let me execute this cell once again, as you can see over here. And item underscore outlet underscore sales of the product in particular store. So as I said, this is the outcome variable to be predicted. We are going to predict this one. This is our target variable that you can see over here, which we are going to predict using these many features that you can see over here. So now let's find shape of our dataset, means number of rows and number of columns available in our dataset. So for that, we have to use shape attribute of pandas data frame. Let me execute this cell. As you can see over here, total we are having these many rows and total we are having this many columns. available in our dataset that you can see over here. Now, pandas, this describe method is used to generate descriptive statistics of a data frame. It provides summary statistics such as count, mean, standard deviation, minimum, maximum, and quartile values for a data frame. For the numerical data in the pandas data frame, let me execute this cell. As you can see over here, count, mean means average value, standard deviation, minimum value, and these are percentile values. And this is maximum value. As I say, it is displaying the statistics only for numerical data available in our pandas data frame, means only for numerical columns. Let me take this particular column. Count in this particular column means total number of rows available in this particular column. As you can see here, less number of rows in compared to this particular value, means some values are missing in this particular column that you can see over here. Average value of this particular column, standard deviation of this particular column, minimum value available in this particular column, item underscore weight. And as I said, these are percentile values, means in this particular column 25% values are below this. In this particular column 50% values are below this. In this particular column 75% values are below this, and maximum value in this particular column. Same for other columns as well that you can see over here. So this way we can get descriptive statistics of a data frame like count, mean, standard deviation, minimum, maximum, and quartile values for the numerical data in the pandas data frame that you can see over here. Now next, here we have to check null values in the data frame, means here we have to check whether our dataset contains some missing values or not. So for that, let me write data which is pointing to our pandas data frame here, and we have to use isNull method of pandas data frame. Let me execute this cell. As you can see here, it is displaying pandas data frame with boolean values that you can see over here. Now let's perform sum of true values that you can see over here. So this statement is used to count the number of missing values in each column of a data frame. It returns a series that you can see over here that shows the count of missing values for each column that you can see over here. From this we can see that these many values are missing in this particular column, item underscore weight, and these many values are missing in this particular column, outlet underscore size. So now let's calculate percentage of missing values for each column in the data frame. So for that, let me write data isNull method dot sum multiply by 100, because we are interested in percentage, divided by length of our data frame. Let me assign it to one variable. You can use any other name as well. And let me print this variable. Let me execute this cell. So as you can see, around 17% values are missing in this particular column, item underscore weight. Around 28% values are missing in this particular column, outlet underscore size, that you can see over here. If missing value percentage is less than 5%, we can drop rows having the missing values. But here you can see it is showing percentages higher than 5%. Here is 17, here is 28. So we have to handle the missing values. Now next, here we have to check for duplicate values, means we are going to check whether our dataset contains some duplicated rows or not. So for that, let me write data dot, we have to use duplicated method of pandas data frame. Let me execute this cell. As you can see here, this statement checks for duplicate rows in the data frame. It returns a boolean series that you can see over here, indicating whether each row is a duplicate, means true, or not, means false. So that's why here it is displaying true or false boolean values. Whether each row is duplicate means true, or not means false, that you can see over here. And let me use dot any. So any is a method applied to the boolean series that you can see over here. It returns true if any of the values in the series is true, indicating the presence of at least one duplicate row in the data frame. Otherwise, it will be false. Let me execute this cell. As you can see over here, you can observe that the output is false, indicating there are no missing values present in the data set that you can see over here. So this way we can check for the duplicated values, means rows available in our data set that you can see over here. So now next, here we are going to handle the missing values. As you can see here, values are missing in this particular column, also in this particular column as well. So we are going to handle these missing values. So let me check this column. Let me copy this column name and let me paste it over here. As you can see over here. Now let me write data and let me copy this column name and let me paste it over here. As you can see over here, item underscore weight is a numerical column and outlet underscore size is a categorical column that you can see over here. So we have to use different strategy to fill the missing values in this particular column, which is numerical, and we have to use another strategy to fill the missing values in this particular column, which is categorical. So let's get started. So let's first fill the missing values available in this particular column, which is numerical. So as I said, first we are going to fill missing values in this particular column, item underscore weight, which is numerical column. So there are two primary approaches for handling missing values in the numerical data. First, univariate imputation, and second, bivariate or multivariate imputation. So what is univariate imputation? Univariate imputation involves filling missing values using only information from the column with the missing data. So we will fill the missing values using the available values in the particular column only. In our case, item underscore weight column only, without considering other columns for this purpose. Common methods for univariate imputation include mean imputation. Filling the missing values with the mean means average of the known values in the column. Median imputation. Filling missing values with the median of known values in the column. Mode imputation. Filling missing values with the mode means most frequent value of the known values in the column, but this particular imputation is not suitable for the numerical data, means for numerical columns. Constant value imputation, filling missing values with some constant value. Interpolation, estimating missing values using the values of the adjacent data points or time points. Now bivariate imputation. Bivariate imputation involves filling missing values using information from other columns as well. Here we are not only considering columns having missing values, but also we are considering other columns as well to fill the missing values in the particular column. In our case, item underscore weight. The imputation is based on the values in both the column with missing data and additional related columns. Common methods for bivariate imputation include regression imputation, predicting missing values using a regression model based on the relationship with other variables or features. K-nearest neighbors imputation, filling the missing values based on the values of the nearest neighbors in a multidimensional feature space. Machine learning based imputation, utilizing machine learning models to predict missing values based on other features in the data set. So these are different approaches for handling missing values in the numerical data. Let's begin by addressing the missing values through the univariate imputation methods. Following that, we will attempt to fill the missing values using bivariate or multivariate imputation methods as well. So let's get started. Let's first use univariate imputation methods to fill the missing values in our column item underscore weight. So let's jump to Jupyter notebook. So let me write data and item underscore weight. Let me execute this cell. As you can see over here, let me find mean of this column and let me assign it to one variable. Mean underscore weight is equal to this statement. Let me copy this and let me paste it over here. Let me use median and let me change it to median. Let me execute this cell. Let me display print mean underscore weight and median underscore weight. Let me execute this cell. As you can see over here, mean of this particular column and median value for this particular column that you can see over here. So now let's fill missing values with mean and median values. So let me copy this and let me use fill NA and let me copy this and let me paste it over here and let me create new column with name item underscore weight underscore mean. Let me copy this and let me paste over here median and let me copy this and let me paste over here. So we are going to fill missing values using mean and median values that you can see over here, and we are creating new columns with these names. We are not updating existing column. This one we are keeping existing column as it is. Let me execute this cell. Let me check. As you can see here, two new columns are created after filling missing values using mean and median. that you can see over here. Now let's check variance after and before filling the missing values using mean and median. So let me write print original weight variable variance. Let me copy this column and let me paste it over here. And we have to use dot var method to find the variance of the original column. Let me copy this. Let me paste it over here and here as well. Let me write proper message item weight variance after mean imputation. Let me copy this. Let me paste it over here. As you can see here, let me copy this message. Let me paste it over here. After median imputation. Let me copy this, our newly created column, and let me paste it over here. Let me execute this cell. As you can see over here, original weight variable variance and item weight variance after mean imputation. Item weight variance after median imputation that you can see over here. So you can observe after applying mean and median imputation, the variance in our data tends to decrease that you can see over here. So reason is simple. When you impute missing values with mean or median, you effectively concentrate those imputed values around the central point, right? This reduces the spread of values across the data set. As more data points are clustered closer to the central value. As I said, after applying mean or median imputation, the variance in our dataset tends to decrease. That you can see over here, 21 to 17. That you can see over here. However, it is important to note that these changes should not result in a drastic alternation of variance, right? As you know, variance in this context signifies the spread or distance of data points from the average value. So just remember, as I said, it is important to note that these changes should not result in a drastic alternation of the variance that you can see over here. Here we can say there is no drastic alternation of the variance, right? That you can see over here. Also, we have to check distribution of the data after and before filling the missing values using mean and median. There should not drastic change in the distribution of the data. Let's check this. So let me copy this original column and let me use plot. Kind is equal to KDE plot and let me use label is equal to original. Now let's plot this after filling the missing values using mean dot plot kind KDE label equal to mean. Let me copy this and let me paste it over here. Let me copy this. Let me paste it over here and median. Let me write plt dot legend plt dot show. Let me execute this cell. As you can see over here, original data distribution in this blue color, mean as you can see here in orange color, and median in this green color that you can see over here. As you can see, after applying mean and median imputation, data distribution has been altered that you can see over here. Most values are clustered around mean and median. This is not desired and needs attention. So we have to do something. Also, let's plot box plot. Let me copy this column name and data and let me paste it over here. Again, let me copy this column name. Let me paste it over here. Again, let me copy this column name. Let me paste it over here and dot box plot. Let me execute this cell. As you can see here, after filling the missing values using mean and median, you can observe a reduction in the spread of the data that you can see over here, which is not desirable that you can see over here. So now let's use another method to fill the missing values in this particular column, item underscore weight. So we are going to use interpolate method of pandas. So again, let me copy this column name. Let me paste it over here. Dot interpolate and method is equal to linear, and let me create new column with name item underscore weight underscore interpolate is equal to this statement. As you can see here, we are applying linear interpolation method to fill the missing values in this particular column item underscore weight. Linear interpolation estimates missing values in dataset by drawing a straight line between two neighboring data points and filling the missing values with the values along that line. Let me execute this cell. Let's use KD plot once again to compare the original distribution of the item weight variable with the distribution after interpolate. So let me copy these two statements and let me paste it over here. So we are keeping as it is original, but here let me copy this, let me paste it over here and let me change label to interpolate and let me write plt.legend and plt.show. Let me execute this cell. As you can see over here, distributions are very close, that you can see over here. After interpolation, that you can see over here. From this, we can say that this method is better to filling the missing values in this particular column, item underscore weight, as compared to our previous methods, mean and median, that you can see over here. Now let's try bivariate or multivariate imputation, and we are going to use k nearest neighbors imputation, knn imputer. So for that, let me write from sklearn dot impute, let me import knn imputer. Let me execute this cell. As you can see here, now our module knn imputer is successfully imported. Let me create instance of knn imputer. Let me set n underscore neighbors to 10, and let me set weights to distance. Let me create instance of this knn imputer with name knn. Let me execute this cell. Now let me use knn dot fit underscore transform on our column item underscore weight. Let me copy this. Let me paste it over here. Again, let me create new column with name knn underscore imputer is equal to this statement. Let me execute this cell. Value error. Okay, so let's flatten the result using Ravel to remove this value error. Let me execute this cell once again. Here we have to use 2D. Let me execute this cell once again. As you can see here, done. So let me tell you something about k nearest neighbor imputer. The k nearest neighbors imputer is a method that can be used to fill missing numerical values in a dataset. It works by identifying the k nearest data points with available values for the missing entry and then compute an average or weighted average of those values to fill the missing entry. This imputation technique is based on the principle that the similar data points often have similar values. So let's use KD plot once again to compare the original distribution of the item underscore weight variable with the distribution after knn imputer. So let me copy these two statements and let me paste it over here. Let me keep this line as it is. Original distribution. Let me copy this. Let me paste it over here and let me change label to knn imputer. Let me write plt.legend and plt.show. Let me execute this cell. As you can see over here, original distribution and distribution after applying knn imputer, that you can see over here. So from these all methods, we can say that linear interpolation is the preferred method for filling missing values in the item underscore weight column, right? As a result, we will retain this column while removing others. So let's remove other columns. So let me write data dot drop and let me drop this original column item underscore weight. Also this columns item underscore weight underscore mean. Let me copy. Let me paste it over here. Also we have to drop this column item underscore weight underscore mean. Let me copy. Let me paste it over here. Also we have to drop this column that just we have created knn underscore imputer, and let me set axis to 1. To modify our existing data frame, let me assign back. Let me execute this cell. Now done. Let me check. As you can see here, now we have this newly created column item underscore weight underscore interpolate, that you can see over here. Now let me check data dot is null dot sum. As you can see, we have successfully filled missing values in this particular column item underscore weight, that you can see over here. Now let's fill missing values in this particular column outlet underscore size, which is categorical column. So in categorical data, we don't have the option to compute a mean or median due to the nature of categorical variables, right? Instead, we have to use the mode, which represents the most frequent value. However, it's important to note that when filling missing values using the mode, we may employ different techniques or strategies depending on the specific context or dataset. So let me write data and let me copy this column outlet underscore size. Let me execute this cell. Let me use value underscore counts method. As you can see over here, we have different outlet size, medium, small and high. But here we can't directly fill missing values using mode. We are going to fill missing values in this particular column, outlet underscore size, based on outlet underscore type. Let me show this. Let me copy this column name. Let me paste it over here. Let me use value underscore counts method on this particular column that you can see here. Outlet type, supermarket type 1, grocery store, supermarket type 3, supermarket type 2. So we are going to fill missing values in this particular column based on outlet underscore type. So let's find mode of outlet size column as per outlet type column. So we are going to calculate the mode, most frequent value of outlet size for each outlet type using pivot table. Let me show this. So let me write data dot pivot table and let me set values of this table with this column and columns of this table with outlet underscore type. And let me use aggregate function lambda x colon x dot mode. And let me take first index. Let me execute this cell. Sorry, func. Let me execute this cell once again. As you can see here, our pivot table. So as I said, this code calculates the mode, most frequent value of outlet size for each outlet type that you can see over here. So this is the most frequent outlet size value in this particular outlet type. This is the most frequent outlet size value in this particular outlet type. This is the most frequent outlet size value in this particular outlet type. This is the most frequent outlet size value in this particular outlet type that you can see over here. So this way we are going to fill missing values in this particular column as per outlet type. Let me assign it to one variable, mode underscore outlet. You can use any other name as well. Let me execute this cell. Let me check, as you can see over here. So now let's identify missing values in outlet size column. So let me write data. Let me copy this. Let me paste it over here. Dot is null. And let me assign it to one variable, missing underscore values is equal to this statement. Let me execute this cell. Let me check. As you can see here, Boolean series having true and false values. True means here values are missing that you can see over here. So as I say, we are going to fill missing values in this particular column, outlet underscore size as per outlet type. So now let's locate these missing values. Let me copy this column name, outlet type over here, and let me use this apply method with lambda x colon this one, mode underscore outlet. Let me copy this. Let me paste it over here and x. As I said, we are going to fill missing values in this particular column, outlet underscore size as per outlet type that we have created over here using this pivot table, this one. And let me assign back missing underscore values in this particular column, outlet underscore size is equal to this statement. Let me execute this cell. Now done. So we have successfully filled missing values in this particular column, outlet underscore size, based on this particular column, outlet underscore type that you can see over here. So as I said, the result of this operation is that missing values in outlet underscore size are filled based on the mode of outlet underscore size corresponding to their outlet type, this one. Now let me check missing values, data dot is null dot sum. Let me execute this cell. As you can see over here, we have successfully filled missing values in this particular column, item underscore weight, and in this particular column, outlet underscore size that you can see over here. Now let's check another column, item underscore fat underscore content. So let me write data dot columns and let me write data, and we have to work on this particular column, item underscore fat underscore content. Let me copy this. Let me paste it over here. Let me execute this cell. Let me use value underscore counts method. As you can see here, low fat, regular, again LF. Again it is representing low fat. As you can see here, REG. This is also representing regular. As you can see, L in lowercase. Again, this is representing low fat. So you can see different variants of low fat and regular. We require consistent labeling for different variants. So let's do this. So let me write data dot replace, and let's use Python dictionary for this. Let me copy this column name. Let me paste it over here. Let me replace this low fat with LF. Let me copy this and let me replace low fat with LF. And let me replace this REG with regular. This one. And to modify our existing data frame, let me set in place to true. Let me execute this cell. Now done. Let me copy this code. Let me paste it over here. Let me execute this cell. As you can see here, now we have consistent labeling for different variants of low fat and regular that you can see over here. So now let's check another column, item underscore visibility. Let me display column names and let me write data and item underscore visibility. Let me copy this column name. Let me paste it over here. Let me execute this cell and let me use value underscore counts method on this particular column. As you can see over here, this column contains 526 zeros that you can see over here. So we are going to handle these zeros as missing values. So let me copy this column name. Let me paste it over here. So first we have to replace these zeros with np.nan. We have already imported numpy as np. From that I am using nan. Here we are replacing 0 with nan, so we can handle this 0 as missing values. Then let me use interpolate and method is equal to linear, and let me create new column with this name, item underscore visibility underscore interpolate. You can give any other name as well. Let me execute this cell. Sorry, EOLATE. Let me execute this cell once again. Sorry for that. Now done. Let me check. As you can see here, we have successfully created this new column. And also let me copy this statement and let me paste it over here. We have not changed original column, so we have to check this column. Let me execute this statement once again. As you can see over here, we have successfully handled zeros as missing values, and also we have filled missing values using linear interpolation that you can see over here. Now let's check distribution after and before interpolation. So let me copy this column name, let me paste it over here and plot kind equal to KDE and label is equal to original. Let me copy this newly created column, let me paste it over here, let me copy this, let me paste it over here and interpolate. Also let me change color to red so we can visualize it properly. Let me write plt.legend. To remove this, let me write plt.show. Let me execute this cell once again. As you can see over here, we can see distributions are very close to each other that you can see over here. So we have successfully handled these zeros available in this particular column, item underscore visibility, that you can see over here. Now let's drop original column, this one, because we have created this column using interpolate, and let me set access to 1 and let me assign back to modify our existing data frame. Let me execute this cell. Let me check. As you can see over here, we have successfully dropped this original column, item underscore visibility, that you can see over here. Now let's check our next column, item underscore type. Again, let me display column names and let me write data and item underscore type. Let me copy this, let me paste it over here, let me execute this cell and let me use value underscore counts. As you can see over here, we have this many item types available in our data set that you can see over here: fruit, vegetables, snake foods, household, and many that you can see over here. So now let's check our another column, item underscore identifier. Again, let me display column names and let me write data and item underscore identifier, this one. Let me copy, let me paste it over here, let me execute this cell, let me use value counts method. As you can see here, this item underscore identifier contains these values, and as you can see, item identifiers start with FD, NC, likewise. And let me use sample as well, 5. Let me execute this cell. As you can see here, item identifier starts with FD, DR, DR, FD. Let me execute this cell once again. As you can see here, FD, NC and DR, that you can see over here. If you see the categories, it looks like being food, drinks and non-consumables. So let's create new column which contains first 2 characters only from this item underscore identifier. So let me write data Let me copy this column name. Let me execute this cell and let me apply lambda function to extract first two characters, this one, from this item identifier to modify our existing data frame. Let me assign back. Let me execute this cell. Let me check. Let me copy this. Let me paste it over here. As you can see over here, FD, NC and DR. As I said, if you see the categories, it looks like being food, drinks and non-consumables that you can see over here. So we have successfully handled this column item underscore identifier. Now let's take our another column outlet underscore establishment underscore year. Let me display column names first and let me check this column outlet underscore establishment underscore year. Let me copy, let me paste it over here. Let me execute this cell. As you can see, this column contains outlet establishment year. So we are going to create new column that shows for how many years the outlet is present. Means we are going to convert these years to age that shows for how many years outlet is present. In short, outlet age as per the current year. So for that, let me import datetime module as dt. Let me execute this cell and let me write dt dot datetime dot today dot year and let me assign it to one variable current underscore year is equal to this statement. Let me execute this cell. Let me check. Let me copy this variable. Let me paste it over here. Let me execute this cell. As you can see here, current year. So now let me use this variable minus data and our column outlet underscore establishment underscore year. Let me paste it over here. Let me execute this cell. As you can see over here, this outlet is 24 years old. This outlet is 36 years old. Let me create new column with name outlet underscore age. So it is showing for how many years outlet is present. Let me execute this cell once again. Let me check. As you can see over here. So now let's drop original column, this one outlet underscore establishment underscore year. Let me copy this. Let me paste it over here. Let me set access to 1 to modify our existing data frame. Let me assign back. Let me execute this cell. Now done. As you can see, our data set contains many categorical columns. So we have to handle these categorical columns. So let's do this. So let's perform categorical data encoding using ordinal encoding. Means here we are going to use ordinal encoding. As you know, machine learning algorithms can understand only numerical values. So categorical data such as labels or categories need to be transformed into numerical representation for machine learning models to process them effectively, right? So that's why here we are going to convert categorical values to numerical values. So machine learning models can process them effectively. As I said, we are going to use ordinal encoding. Ordinal encoding is a way to assign unique numerical values to each category. So the question is, why ordinal encoding? Can we use label encoding here? Let's check what sklearn is telling about this. As you can see here, currently I am on sklearn.org and label encoder. Encode target labels with value between 0 and n classes minus 1. Please read it carefully. Encode target labels. So this transformer should be used to encode target values y and not the input x. So here we are going to perform encoding on input variables, not on the target variable. That's why here we are using ordinal encoder in place of label encoder. As you can see, sklearn is telling this transformer means this label encoder should be used to encode target values means dependent variable, not the input means not the independent variables. So that's why here we are using ordinal encoder, not label encoder. So for that, let me import from sklearn.preprocessing. Let me import ordinal encoder. Let me create copy of our data and let me store in data underscore encoded is equal to this statement. Let me write data dot select underscore d types. So we are going to select only categorical columns. And let me use include object columns only and columns to fetch column names and let me assign it to one variable cat underscore pulse is equal to this statement. Now let me use for loop. So for call in cat underscore calls, let me create instance of ordinal encoder with name OE. You can use any other name as well. And let me write OE dot fit underscore transform on data underscore encoded and on categorical columns. This one. Let me assign back data underscore encoded call is equal to this statement, and let me print categories as well. Let me execute this cell. As you can see over here, we have successfully performed ordinal data encoding that you can see over here. Let me check data underscore encoded dot head, as you can see over here. Now let's store independent variables in matrix X and dependent variable in vector Y. So let me write data underscore encoded dot drop, and let's drop our target column item underscore outlet underscore cells that we are going to predict. And let me set axis equal to 1 and Y, our target column, into vector Y. Let me execute this cell. Let me check. As you can see over here, our independent variables, and let me check our dependent variable that you can see over here. Item underscore outlet underscore cells that you can see over here, that we are going to predict. Now next, as you know, we are dealing with a continuous target variable, right? Which makes it a regression problem. To tackle this, we are planning to use two regression models, random forest regressor and extreme gradient boosting random forest regressor. You can experiment with additional models if you want. So let's start with random forest regressor. For that, let me import from sklearn.ensemble. Let me import random forest regressor. Also from sklearn.model underscore selection, let me import cross val score because we are going to perform cross validation. Let me create instance of random forest regressor with and underscore estimators 200 and random underscore state. Let me set it to 42 and let me create instance with name RF. Now let's perform cross validation. Instance RF X, our independent variables and our dependent variable, and we are going to perform five-fold cross validation with scoring R2 R square score, and let me assign it to one variable scores is equal to this statement, and let me display average value of this score after five-fold cross validation. Let me execute this cell. It will take some time. We have to wait. As you can see, random forest regressor with R square score 55.42 that you can see over here. Now let's check XGBRF regressor. So for that, let me import from XGBoost. Let me import XGBRF regressor, and we have already imported this cross underscore val underscore score. Let me create instance of SGBRF regressor. Let me set n underscore estimators to 100 and random underscore state to 42, and let me create instance with name xg. Again, let me copy this code. Let me paste it over here. Let me change instance to xg. Again, we are using five-fold cross validation with R2 score, and here we are displaying average value of this score after five-fold cross validation. Let me execute this cell. Again, it will take some time. We have to wait. As you can see here, XGBRF regressor R square score 59.45, as you can see here. So from this result, we can say that XGBRF regressor is the best model for this dataset that you can see over here. So now let's check feature importance of this XGBRF regressor. So again, let me copy this statement. Let me paste it over here. Once again, we are creating instance of XGBRF regressor, and let me write xg.fit on x and y, our independent variables and our dependent variable. Let me assign it to one variable xg1 is equal to this statement, and let me create one pandas data frame, and let me use Python dictionary to create pandas data frame with key feature x dot columns and xgbrf importance xg1 dot feature underscore importance underscore, and let me sort underscore values by this as per the feature importance of XGBRF, and let me set ascending to false. We want to display values in descending order. Let me execute this cell. As you can see here, attribute error. Sorry, here we have to write S. Let me execute this cell once again. As you can see here, feature importance of XGBRF regressor that you can see over here. You can see feature importance score of XGBRF regressor. So I am going to consider first 5 features only. This one, outlet underscore type, item underscore MRP, outlet underscore age, outlet underscore identifier, and outlet underscore size that you can see here with higher scores that you can see over here. So let's drop other columns. As you can see here, I have created list of columns that we are going to drop. This many columns. Now let's check R square score after dropping these columns. So let me write x dot drop, and also let me use this instance xg1, this one that just we have created, and let me copy this list. Let me paste it over here. Let me set axis to 1. Let me execute this cell. As you can see over here, R square score, and also we can see improvement in R square score after dropping these many columns that we have decided after checking feature importance of XGBRF that you can see over here, previous R square score and current R square score that you can see over here. So now let's create our final data frame after dropping these columns. So let me create final data is equal to x dot drop. Also you can copy this as well. Let me copy and let me paste it over here, and let me write columns equal to this. Let me end this, and axis equal to 1. Let me execute this cell. Let me check final underscore data. As you can see here, this is our final data set after feature importance. So let's train our best model XGBRF on entire data set, means on our final data set, this one. So once again, let me import from XGBoost. Let me import XGBRF regressor. Let me execute this cell. Now let me create instance with name xg underscore final is equal to XGBRF regressor. Let me execute this cell. Now let's train our XGBRF on our final data set Y. Our final data set, this one. Let me execute this cell as you can see over here. Now let's check MAE, mean absolute error, as well for our XGBRF regressor. So for that, let me import from sklearn dot model underscore selection. Let me import train test split, and from sklearn dot matrix, let me import mean underscore absolute underscore error. Let me execute this cell. Now let me use train test split on final underscore data Y, and let me set test size to 0.20. We are keeping aside 20% data for testing purpose, and let me set random underscore state to 42, and let me create x underscore train, x underscore test, y underscore train, and y underscore test is equal to this statement. Let me execute this cell. Now let me use this instance xg underscore final, and let's train on our training set x underscore train and y underscore train. Let me execute this cell, and let's perform prediction on our unseen samples available inside x underscore test, and let me assign result to y underscore spread. Let me execute this cell. Now let's check mean absolute error. Let me press Shift tab to check the docstring of this mean absolute error. As you can see here we have to pass actual values and here predicted values by our model, this one. So our actual values are available in y underscore test and predicted values by our model in y underscore spread. Let me execute this cell. As you can see here, this is our MAE, mean absolute error. So as you can see, our mean absolute error is around 714.42, means that on average the absolute difference between the predicted values and the actual values is 714.42. In practical terms, this suggests that the model's predictions are on average off by approximately 714.42 units from the actual values, not necessarily exactly 714.42, approximately 714.42. Now let's perform prediction using unseen samples. So here I have created NumPy array with some values. Let me uncomment this, and let's use this instance xg underscore final to perform prediction. Let me execute this cell. As you can see here, our prediction by our model. As I said, our MAE is 714.42 approximately. So we can also perform prediction like this. Before that, let me assign it to one variable pred is equal to this statement, and we can write another way. Cells value is between pred, which is this prediction, minus 714.42, and let me copy this, let me paste it over here, and plus. So our cells value is between this and this. So either you can perform prediction like this directly. Also we can show result like this to the user as well, that you can see over here. Cells value is between this and this, that you can see over here. So this way we can perform prediction on unseen data using our best model XGBRF, that you can see over here. Let's remove this bracket. So here let me use index 0, this one. Let me execute this cell, and let me execute this cell as well, as you can see over here. Cells value is between this and this. So now let's save our model using joblib. So again and again training is not required, and we can perform prediction using this saved model. So let me import joblib. Let me execute this cell. As you can see here, now our joblib library is successfully imported, and let me save our model. So we have to write joblib.dump our model instance xg underscore final and model name. You can give any name that you want. Let me execute this cell. As you can see here, now our model is successfully saved with this name. So in future we can perform prediction using this save model. Let me show you this. So for that we have to write joblib.load to load our saved model. Let me copy this name, let me paste it over here, and let me give one instance model. Let me execute this cell. Here I have created numpy array with unseen samples. Let me uncomment this, and let me execute this cell. As you can see over here, this way we can save our model, and this way we can perform prediction using our saved model, that you can see over here. Also you can print answer in this way. Let me assign this into variable pred is equal to this statement and index 0. Let me print this, that you can see over here, and again we can use this statement. Here I am directly using cells value is between this and this. You can also use some meaningful message as well. Let me execute this cell, as you can see over here. So this way or this way we can show predictions to the user, that you can see over here. As you can see here, I have created GUI for this project exactly same way as I have created for our previous projects. You can download this code from my GitHub account. Link is given in the description of this video. Now let's perform prediction using this GUI. So let me enter these values. Outlet identifier, outlet size, outlet type, and here outlet establishment year, this one. Let me press this button predict, as you can see over here. This way user can perform prediction using this created GUI. So this way we can perform big Mart cells prediction using machine learning, that you can see over here. Hope you like this video. Please don't forget to subscribe this channel. If you like this video, smash that like button. Thank you very much for watching this video. Take care. Bye bye. See you in the next video.